In clinical neurology, a chronic neuroinflammatory state, whether it's autism spectrum disorder or a sudden onset condition like PANS, is traditionally diagnosed as a permanent hardware deficit. The medical consensus assumes the biological architecture is structurally damaged. That assumption creates an immediate logical contradiction. If a processor's physical hardware is permanently destroyed, the system cannot temporarily fix itself. Yet caregivers and physicians frequently document sporadic moments of extreme lucidity, unprompted eye contact, or sudden symptom remission. The Zolbeden paradox provides the empirical baseline for challenging this model. The premise involves a patient in a permanent, locked-in state following a massive stroke or traumatic brain injury. Physicians administer Zolbeden, a standard over-the-counter sedative. The central nervous system depressant wakes the dormant brain up. For a brief window of time, the patient regains the ability to speak, track objects, and execute motor control. A sedative cannot instantly regenerate dead neural tissue. Instead, the sudden arousal indicates the functional modules required for language and movement remained intact, but were buried under a dense layer of internal noise. The patient appears offline because the internal system is operating at maximum capacity, entirely overwhelmed by its own high-gain, inflammatory defense mechanism. This specific pharmacological response suggests that locked-in states are a failure of gain control. In an engineering framework, the primary barrier to recovery is not biological death, but signal saturation. Optimizing a failing neurological system requires a shift in perspective. We must view the brain as it operates, a high-frequency communication bus of coupled oscillators that requires dynamic equilibrium to function. The mechanical root of neurodevelopmental dysfunction is a specific diagnostic condition called the hysteresis latch. In electronics, hysteresis occurs when a system remains stuck in a specific mode, even after the external trigger is removed. In the human processor, a historical biological impulse event, like a severe viral infection or an environmental toxin, forces the system's logic gates into a permanent defensive posture. To protect the hardware, the system recalibrates its baseline sensitivity to a maximum gain setting. Long after the original biological threat has passed, the circuit remains latched in this high-alert configuration, unable to find the off switch. The human processor exists in an active defensive latch, where every normal piece of environmental data is processed as a critical threat to system integrity. This diagram represents the neurovascular unit, the integrated CPU triad of the brain. To process reality accurately, these three specialized hardware nodes must remain perfectly synchronized. Node 1 contains the microglia. These cells operate as the system's security logic and maintenance drones. In a healthy state, they actively repair connections and only briefly toggle into an alert state to neutralize minor threats. Node 2 consists of the astrocytes. They manage the system's signal clearance. After a neuron fires a pulse of glutamate, the brain's primary excitatory signal, the astrocytes vacuum up the residual data to clear the bus for the next incoming signal. Node 3 is the physical infrastructure, neurons and myelin. The neurons act as the data cables, while the myelin sheath provides the dielectric insulation necessary to transmit high-speed data without the signal leaking into surrounding pathways. When the hysteresis latch is triggered, the microglia in Node 1 stay in a permanent attack state. This locks the entire triad out of synchronization. The astrocytes fail to clear the data bus, and the physical insulation rapidly degrades. A failure in the CPU triad means the brain loses its ability to regulate internal voltage. This ensures a violent collision between incoming sensory data and internal biological noise. In this latched attack state, the brain continuously releases an inflammatory cytokine called TNF-alpha. In engineering terms, TNF-alpha is the processor's master gain knob. This high gain setting forces a constant glutamate leak from the neurons, flooding the entire communication bus with excitatory static. This chart illustrates signal saturation. The block of red static represents the internal noise floor. Because the system is latched in defense mode, that noise floor rises until it consumes almost all available processing capacity, leaving zero voltage headroom for normal operations. When a standard environmental input, like the hum of a refrigerator or the texture of a shirt, enters the saturated system, the input wave instantly hits the hardware ceiling. the clipped waves multiply and distort, filling the diagram with jagged, chaotic square waves. In the middle of a meltdown, an autistic child's processor is physically unable to isolate a human voice from a system saturated with clipping errors. The long-term architectural consequences are severe. While the microglia are locked in their high-alert attack state, all routine background maintenance comes to a complete halt. Synaptic pruning fails. The high noise floor creates a high-impedance rat's nest of unoptimized wiring. Chronic oxidative stress thins the myelin insulation. Without adequate dielectric shielding, signals arc and bleed directly into adjacent pathways. Operating a processor where a motor command crosses wires with a visual input creates constant logic jitter. The system adapts through stochastic resonance. By executing repetitive, high-amplitude motor actions, commonly called stimming, the user injects predictable white noise directly into the circuit. Stimming serves as a mechanical workaround. The hardware manually generates a physical frequency powerful enough to ground the chaotic internal static and stabilize a weak signal. Until the internal architecture is physically pruned and re-insulated, the user relies on stochastic resonance to process reality. Restoration requires a systemic gain adjustment. We have to provide the hardware with the specific metabolic tools to lower its internal volume. This visualizes the implementation of the technical stack. The first gauge represents inositol. It acts as a metabolic signal pad, limiting the electrical current to suppress intracellular voltage surges and restore the hardware's headroom. The second gauge represents NAC and rutin. These compounds serve as the system's heat sink and logic override, directly absorbing thermal noise while manually turning down the TNF-alpha master gain knob. The third gauge is choline. This provides the raw lipid materials required to refurbish the dielectric insulation, physically wrapping the leaky neural chassis to halt signal crosstalk. As this artificial shielding lowers the noise floor below the processor's critical security threshold, the internal alarm finally stops ringing. This quiet environment breaks the hysteresis latch, allowing the microglia to toggle out of attack logic and resume the delayed process of synaptic pruning. Providing metabolic padding, coolant, and insulation manually recreates the zolpidem effect. We drop the internal static low enough for the brain's original signal to emerge. Executing this recovery relies on the black box mandate. The human processor possesses too much hardware variance for static medical dosing tables to be effective. We manage recovery by manipulating inputs and observing the direct outputs. Decoding behavior into diagnostic trouble codes, or DTCs, allows us to pinpoint specific subsystem failures. Looking at this master telemetry table, explosive meltdowns are classified as a DTC for signal clipping. The hardware voltage rails are at maximum capacity. The root cause analysis dictates increasing the signal pad, inositol, to turn down the amplitude and restore headroom. Alternatively, a state of lethargy or regression is a DTC for a kernel stall. The background operating system lacks the resources to clear cellular waste, requiring a targeted reload of B12 and folinic acid to restart background garbage collection. Decoding behavior into telemetry allows caregivers to calibrate the high-performance processor as lead engineers. During the active flush phase, as pathogens are debrided from the logistics hub, the body releases a massive exhaust surge of dirty current into the bloodstream. If this surge hits the brain without adequate shielding, it triggers a system trip, clinically known as a Herxheimer event. The processor hits a hard thermal limit, manifesting as an acute fever or physical rash. The engineering fix involves throttling down the debridement inputs while maintaining the coolant shield until the telemetry normalizes. The speed of the hardware reset is limited by the system's capacity to exhaust the waste. Recovery involves systematically lowering the noise floor until the processor's inherent logic can execute its own automated repair sequences. When the rat's nest is pruned and the hysteresis latch is broken, the brain achieves laminar flow, possessing the vast, quiet voltage headroom necessary to process the infinite data load of reality.